A motor is a device that converts electrical energy into mechanical energy. This mechanical energy is in the form of a turning motion. The turning motion can be used to drive a load that is coupled to the motor. The turning motion is produced by the interaction of magnetic fields that are created in the motor. When two magnetic fields interact, they can cause an object, such as the rotating part of a motor, to move. This movement is called motor action. We can use this simplified illustration to see how motor action occurs in a DC motor. In this illustration, the rotating part of a DC motor, called the armature, is represented by a loop of wire. The loop of wire is positioned in the magnetic field created by two permanent magnets. The loop is connected to a DC power source, which is not shown. As current flows from the negative side of the DC power source through the loop to the positive side, it produces a magnetic field around the wire. The poles of this magnetic field are perpendicular to the loop. The North Pole is here, and the South Pole is here. In order to show how the magnetic field around the loop interacts with the magnetic field of the permanent magnets, we'll represent the poles of the loop with a bar magnet. The bar magnet is pivoted so that it's free to rotate. With the bar magnet in this position, the two north poles are next to each other, and the two south poles are next to each other. The like poles repel each other, so the interaction of the magnetic fields causes the bar magnet to rotate. The rotation or movement of the bar magnet is an example of motor action. As the bar magnet rotates, the repelling forces decrease because the like poles are getting farther apart. The bar magnet's north pole is attracted to this permanent magnet's south pole, and the bar magnet's south pole is attracted to this permanent magnet's north pole. The attracting forces increase as the unlike poles get closer to each other. So when the unlike poles are closest to each other, the attracting forces are the greatest. At this point, the bar magnet would stop unless it had enough momentum to carry it past the poles of the permanent magnets. To keep the bar magnet rotating, the polarity of either the bar magnet or the two permanent magnets must be changed. In a DC motor, what is changed is the polarity of the armature, which is represented by the bar magnet in this example. To see how this is done, we'll again use a loop of wire to represent the armature. And we'll add two components called brushes, and a conducting ring known as a commutator. The brushes are connected to the DC power source. The commutator is mounted on the end of the armature so that it can make sliding contact with the brushes. The commutator is not a solid ring. Instead, it consists of conducting segments that are separated from each other. With this arrangement, current flows from the negative side of the DC power source through one brush to a commutator segment. From the commutator segment, the current flows through the armature in this direction. It then flows through the other commutator segment to the other brush, and then to the positive side of the power source. The current flow through the armature creates a magnetic field. The interaction between this magnetic field and the magnetic field produced by the two permanent magnets causes the armature to rotate. In other words, motor action is produced. In this topic, we looked at how to disassemble, inspect and clean, and reassemble a DC motor. Try some practice questions now that relate to this material. Even though the armature has turned, the current still flows from the negative side of the power source through the armature to the positive side of the power source. However, the commutator has physically changed the direction in which the current flows through the armature. This change in direction changes the polarity of the armature's magnetic field. So, the brushes and the commutator in a DC motor enable the armature to change its magnetic field, and as a result, the armature continues to turn. The example we just saw was simplified to help make things clear. Both the construction and the operation of actual DC motors are more complex. For example, instead of a magnetic field created by permanent magnets, A DC motor usually has a magnetic field created by electromagnets called field coils. Now, one of the forces created during the operation of a DC motor that you should be aware of is known as armature reaction. Armature reaction is a movement or shift in the magnetic field created by a DC motor's field coils that is caused by the rotation of the armature. Unless armature reaction is compensated for, it can result in damage to the motor's brushes and commutator. To compensate for armature reaction, pieces called interpoles are installed between the field coils in many DC motors. Magnetic fields created around the interpoles oppose any shift in the magnetic field created by the field coils. Take a moment now to answer a question about the basic principles of DC motor operation. This is a typical DC motor that has been disassembled so that its parts can be identified. The first part we'll look at is the motor's frame, which is also called the yoke. The frame supports all of the other motor parts and is the part generally used to mount the motor on its foundation. These are the main field poles. They consist of coils, which are the motor's field coils, wrapped around the iron cores called field pole pieces. The field coils are electrically connected to a DC power source. The field pole pieces are usually bolted to the frame. Main field poles are always in north-south pairs. The armature is the entire rotating assembly. It includes the shaft, the armature core, the armature windings, and the commutator. The shaft supports the armature and allows it to turn. The armature core supports and houses the armature windings, which are the current-carrying conductors. The armature windings are connected to the commutator. The points on the commutator where the actual connections between the windings and the commutator segments are made are called risers. The risers are protected by and held in place under a wrapping of varnish-coated fibers. Current flows from one commutator segment through the armature and back through another commutator segment. The commutator makes sliding contact with a set of brushes. The brushes, which are fitted into holders, are held against the commutator by brush tensioning devices. The brushes provide a path for current flow from the power source to the commutator. Attached to the brush holders are brush pigtails, which serve as the connection points between the brushes and the brush holders. The brush holders are supported by brush rigging. Most DC motors have one set of brushes for each main field pole. There is a negative brush for each south pole and a positive brush for each north pole. In addition to the main field poles, this motor also has interpoles to help compensate for armature reaction. As is usually the case, an interpole is smaller than a main pole piece, and it has a coil wound around it. The interpoles are bolted to the frame. The motor's end bells have two functions. They support the brush rigging, and they also house the bearings that support the armature. The end bells are bolted to the motor's frame. Now that we've identified the parts of a typical DC motor, let's look at how DC motors can be classified. There are three basic types of DC motors: series motors, shunt motors, and compound motors. These classifications are based on the way that the field coils in each motor are connected to the armature. The external appearance of all DC motors is very similar, but there are several ways to distinguish one type of motor from another. For example, this is a nameplate from a typical DC motor. The entry in the block labeled wound identifies the type of motor it is. In this example, the block contains the letters CPD, which means that the motor is a compound motor. You can also determine what type a motor is by referring to a schematic diagram in the manufacturer's manual. This schematic diagram represents a series motor. In a series motor, the field coils, which are also referred to as the series field, are connected in series with the armature. So, in a series motor, there is only one path for current flow. Each coil in a series field is usually made of a few turns of large wire. so series fields have very low resistance. In this type of motor, the armature also has a very low resistance, so the current flow through the motor is very high. This schematic uses standard markings to identify the fields in the motor. The letter S means series, and the letter A means armature. The leads from the series field in this example are marked S1 and S2, and the armature is marked A1 and A2. The numbers following the letters indicate the direction of current flow, which is from 1 to 2. For example, A1 could be assumed to be negative, and S2 could be assumed to be positive. The primary purpose of the markings is to ensure that when the motor connections are made, current flow through the motor will be in the proper direction. The same markings are used to identify the motor's leads, so you can also determine what type of DC motor is by examining its leads. Now, this is a schematic of a typical shunt motor. The letter F means shunt, so the shunt field is marked F1 and F2, and the armature is marked A1 and A2. In a shunt motor, the field coils and the armature are always connected in parallel with each other. So in this particular motor, there are two paths for current flow. Each coil in a shunt field is usually made of many turns of fine wire, so the resistance in the shunt field is very high. Because the resistance of the armature in a DC motor is very low, it's important to always install resistance in series with the armature before starting a shunt motor. If full-line voltage were applied to a shunt motor that did not have resistance installed in series with the armature, the resulting high current flow could severely damage the armature. Once the motor is up to its operating speed, the series resistance can be disconnected or bypassed. Now, this is a schematic of a typical compound motor. Compound motors are the most commonly used type of DC motor, and they are also the most complex because a compound motor contains two types of fields, a series field and a shunt field. The field coil markings and armature markings in the schematic show that the series field is connected in series with the armature, and the shunt field is connected in parallel with the armature. So there are two current paths in this motor. Take a moment now to check your knowledge of DC motors. In this topic, we looked at the basic principles behind the operation of DC motors. We also identified the basic parts of a typical DC motor, and we looked at how you can identify different types of DC motors. Take a moment now to try some practice questions that relate to this material. Brushes make the electrical connection between the power source and the commutator in a DC motor. Brushes are usually made of carbon, and the size of a particular brush is determined by the amount of current it has to carry. Many of the problems that occur in DC motors originate in the brushes or in the brush rigging assembly. Two main causes of brush problems are wear and damage, both of which can be caused by improper adjustments. To do their job properly, the brushes must make full flat contact with the commutator at all times. This contact may not be possible if the brushes are hung up in the brush holders, if the brush pigtails bind on the brush holders, if the brush tensioning devices are set incorrectly, or if the brushes are too short. Full contact between the brushes and the commutator is also impossible if the brushes are broken, cracked, or chipped. When cracks or chips reduce the surface area of the brush, current has to flow through a smaller area. This may cause sparking or arcing between the brush and the commutator, and the brushes may heat up. The sparking may be minor, or it may be extreme, causing what looks like a ring of fire around the commutator. Sparking always indicates a problem in motor operation. Now, here's an example of a good brush, one that's not worn or damaged. The surface of the brush is not chipped or cracked, and it is smooth and shiny. The shape of the brush conforms to the shape of the commutator, and the brush is not too short. This brush pigtail is also in good condition, and it's securely fastened to the brush. Now that we've examined some problems commonly associated with brushes, and we've seen what a good brush looks like, Let's see what's involved in maintaining brushes and brush rigging. To begin, the power to the motor is shut off, and the motor is locked and tagged according to plant procedures. The motor in this example has been taken to a shop for maintenance. The first step in any motor maintenance procedure is cleaning the motor. The inspection doors are opened, and the interior of the motor is vacuumed to remove as much loose dirt and carbon dust as possible. After the vacuuming, an approved cleaning solvent and a brush are used to wipe out the interior. Whenever you use cleaning solvents, be sure to follow all applicable safety precautions, such as wearing the proper gloves to protect your hands. During the cleaning step, it's important to pay special attention to the brush holders, the brush tensioning devices, and the commutator. The brushes can be removed from their holders so that the inside of the holders can be cleaned. Cleaning the commutator also involves cleaning the area between the segments. Care must be taken to ensure that the brown coating on the segments is not removed. This coating aids current flow between the brushes and the commutator when the motor is operating. After the interior of the motor has been thoroughly cleaned, the next step is to inspect the brushes and the brush rigging. The brush rigging includes the brush holders and the brush tensioning devices. The surfaces of the brushes should be checked for damage and wear. A brush that is damaged or worn down to 1/4 of its original length should be replaced. The brush pigtail should be securely fastened to the brush. The pigtail should be flexible, and it should not be frayed or discolored. The inside surfaces of the brush holders should be checked to make sure that they're clean and smooth. Any burrs or dings must be removed with a file or sandpaper. If they're not removed, a brush could get hung up on them and not make good contact with the commutator. The bottom edges of the brush holders should also be smooth, straight, and free of burrs. If they're not, the edges must be smoothed with a file or sandpaper, or the brush holders must be replaced. Most brush holders can be adjusted, so it's very important to make sure that they're positioned properly. Brush rigging may also need to be adjusted. The brush rigging is adjusted by loosening the brush holder bolts and then moving the holders so that the brushes cover as much area as possible. After the rigging has been adjusted properly, the brushes can be replaced if required. If new brushes are being installed, they must be the right type and grade for the motor as specified in the motor manufacturer's manual. The brushes must be properly seated in their rigging. In other words, the shape of the brush's bottom should fit the shape of the commutator. Your facility may have specific procedures for you to follow when you're seating new brushes in their rigging. If no procedures are specified, there are several that can be used. For example, one way is to seat brushes using extra fine flint paper to alter the shape of the brush. When this method is used, a strip of flint paper is torn off that is at least as wide as the brush. The strip of flint paper is then placed on the commutator with the flint side out. The brush is placed in the brush holder, and the tensioning device is adjusted to hold the brush tightly against the flint paper. In this example, the motor's armature is then turned slowly back and forth a few times. The brush is then removed and inspected to see if it has the same shape as the surface of the commutator. If it doesn't, the procedure with the flint paper is repeated. When the shape of all of the brushes conform to the shape of the commutator, the seating procedure is complete. All traces of carbon dust must then be removed from the motor. The next step is to install the brushes. After they're placed in the brush holders, the brushes are moved up and down to make sure that they can move easily. The next step, if necessary, is to set the amount of tension applied by the brush tensioning devices. The tensioning devices in this example are set by the factory and are not adjusted. Take a moment now to check your knowledge of brushes and brush rigging. The purpose of a commutator in a DC motor is to provide the sliding connection points from the brushes to the current-carrying conductors in the armature. A commutator in good condition has a smooth, highly polished surface. Commutators generate a film over their surface that aids the current flow from the brushes to the commutator. The color of this film ranges from a light brown to a chocolate brown when the commutator is in good condition. Care must be taken to avoid removing this film as the commutator is being cleaned. If the film is removed, commutator efficiency will decrease and the brushes may wear more rapidly. Many commutator problems are caused by problems with brushes. Commutator problems can be kept to a minimum by keeping the motor clean and by correcting brush problems as soon as possible. There are three general areas of a commutator that require thorough cleaning on a periodic basis. The three general areas of a commutator that require thorough cleaning on a periodic basis are the surface of the commutator, including the area between its segments, the bearing end of the commutator, and the area behind the risers. When the motor is running, the commutator surface can be cleaned with a canvas wiper or a commutator stone to remove dirt and other contaminants without removing the protective film. Before any other cleaning, though, the motor must be stopped and locked and tagged according to procedures. In this example, the motor is taken to a shop for further cleaning. Then the area between the commutator segments can be cleaned. This area is likely to collect dust, brush chips, copper flakes, and other particles. A good light makes it possible to check this area visually. The mica that is used to insulate the segments from one another ranges in color from light gray to white when it is clean. A soft brush and a vacuum hose are good tools to use to remove any particles between the segments. In addition, hand slotters or scrapers are tools specifically designed to remove excess mica and foreign particles and to smooth the edges of the commutator segments. The bearing end of the commutator and the area behind the risers should also be cleaned until all dirt and dust are removed. Now that we've looked at how a commutator can be cleaned, let's identify some problems that can occur in commutators. Typical problems include threading, grooving, copper drag, and flashover. Take a moment now to check your knowledge of commutator maintenance. In this part, we'll look at general procedures for troubleshooting a DC motor, and we'll see how to test for grounds, opens, and shorts. The motor to be checked should be de-energized, locked out, and tagged according to approved procedures. Troubleshooting a de-energized motor helps prevent personal injury and protects the motor and the test equipment from damage. The motor in this example has been taken to a shop for troubleshooting. First, it should be checked carefully for any obvious problems, such as broken wires, loose screws, short brushes, and charred insulation. The brushes and the brush rigging should also be checked. The armature and field windings are also checked. It's common practice to look for grounds, opens, and shorts. These are the problems that occur frequently in all types of electric motors and can prevent them from operating. A ground is a breakdown in insulation that provides a current path to ground where there should not be a path. An instrument commonly used to check for grounds is a meg-ohm meter. Meg-ohm meters are available in several designs. Some are powered by a hand-crank generator, others are line-powered, and others are battery-powered. The one used in our example is battery-powered. Before a meg-ohm meter is used to test for grounds, it should be tested to make sure that it's operating properly. Begin by clipping the meter's two probes together and operating the meter. The meter should indicate 0 resistance. Next, separate the probes and operate the meg-ohm meter again. This time, it should indicate infinite resistance. The digital readout on this meg-ohm meter indicates infinite resistance by displaying a blank readout except for the number 1, which appears all the way to the left. Finally, connect both probes to ground and operate the meter. This time, the meter should indicate 0 resistance. If the meg-ohm meter is operating properly, it can be used to test the de-energized motor. First, the motor's 3 leads are connected together. Then the megohm meter's ground lead is attached to a metal section of the motor, and the meter's line lead is connected to the motor leads. This arrangement provides a current path to ground if the motor is grounded. If the meter indicates the expected normal resistance reading for the leads, there is no ground present. A reading of 0 or nearly 0 indicates that there's a ground somewhere in the motor. In order to determine exactly which part or parts are grounded, further tests must be made using the process of elimination. In other words, one circuit at a time must be tested to eliminate those that are not grounded. For example, the compound motor represented by this diagram has three separate circuits: the series field, the shunt field, and the armature. Each circuit must be tested individually, and then each part in any grounded circuit must be tested separately. First, the electrician raises the brushes off of the armature to separate the three circuits. Then he uses the megohm meter to test each circuit separately. To test the series field, the electrician attaches the meter's ground lead to the motor's metal frame, and the meter's line lead to the S lead. When the electrician operates the meter to make the test, it shows a normal resistance reading for the series field. This means that the entire series field can be eliminated. There are no grounds in this circuit. To test the shunt field, the electrician moves the meter's line lead to the F lead. The meter's ground lead remains attached to the motor's metal frame. When the electrician operates the meter for this test, it shows a reading of almost 0 resistance. The next step is to test the armature. To do this, the electrician attaches the meter's ground lead to the shaft of the motor and holds the meter's line lead against the commutator. The electrician then operates the meter, and this time it indicates a normal resistance reading for the armature. There is no ground in the armature circuit, so the entire armature assembly can be eliminated. At this point, both the series field and the armature have been eliminated from consideration, and troubleshooting is focused on the shunt field. The next step is for the electrician to disassemble the motor and find out where the ground is in the shunt field. After the motor is disassembled, the connections between the field coils can be broken, and each coil can be tested individually. Any bad coils that are found can be replaced, and then the motor can be reassembled, tested, and returned to service. Now, another common problem that can be found in a DC motor is an open. An open is a break that stops current flow somewhere in a circuit. To check for opens in a DC motor, the motor is de-energized, locked out and tagged, and then each circuit is tested individually from end to end with an ohm meter or a multimeter that's set to measure resistance. For example, this compound motor diagram shows two paths for current flow: a shunt field circuit and a series field circuit. To separate these two circuits and the armature circuit, the motor's brushes are lifted off of the commutator. We'll test the shunt field circuit first. According to the diagram, the shunt field must be read from motor lead F1 to motor lead F2. On the diagram, the F1 lead is also marked A1 for the armature circuit. But this is not a problem because the armature circuit was disconnected when the brushes were lifted off of the commutator. So to test the shunt field, one ohm meter lead is connected to motor lead F1 and the other ohm meter lead is connected to motor lead F2. We'll say that the ohm meter indicates very low resistance, which means that there is no open in this circuit. A high resistance reading would have indicated an open in the circuit. The series field is checked next. According to the diagram, the series leads are S1 and S2. The diagram also indicates that S1 is connected to the brushes, but it does not indicate which brush, the negative brush or the positive brush. To determine which brush is connected to S1, one of the ohm meter's leads is connected to S2, and the other lead is connected to a lead connection on one of the brush holders. We'll say that the meter does not show a reading, so either there is an open in the series field, or the meter lead is connected to the wrong brush holder. To check further, the meter lead is moved to the other brush holder. Now we'll say that the meter indicates a low resistance reading, so the second brush holder is the right one, and the series field is not open. At this point, it has been determined that there is no open in the series field circuit, and there is no open in the shunt field circuit. However, the series field has only been eliminated as far as the brushes, so the next step is to check the brushes. To check a brush, 1 ohm meter lead is placed on the brush pigtail, and the other lead is placed on the commutator segment directly under the brush. If there is a reading, the brush is all right. If there is no reading, there is an open. In this case, we'll say that there is a reading, so this brush is all right. The same check is then repeated for the other brush. This time, we'll say that there is no reading, so this brush is faulty. A detailed check is then performed on the faulty brush and on the commutator. The brush is removed, and the brush's pigtail, the brush length, the brush's contact surface, the inside of the holder, and the bottom of the holder are all examined. In this example, the brush has worn down and it's too short. Then the commutator is inspected for dirt, contaminants, and general color. In this case, the commutator looks all right. Since the brush is too short, it is replaced with a brush of the proper size and grade. After the brush has been properly seated, it is tested. In this case, the ohm meter shows a reading, so the new brush is all right. The next step is to test the entire circuit that includes the series field, the armature, and the brushes to see if the open has been repaired. We can use the diagram to identify a current path that allows this to be done. The shunt field has already checked out all right, so it can be bypassed. So, according to the diagram, 1 meter lead should be placed on motor lead F1A1, and the other lead should be placed on motor lead S2. The current path being tested is from motor lead S2 through the series field to S1A2, through the brush, through the armature and the other brush, to F1A1. If the meter shows a reading, we'll know that the series field, the armature, and the brushes are good, and that the problem has been solved. The last motor problem we'll look at is a short. A short occurs when there is minimum resistance through a component and maximum current flow. The excess current generates heat in the component, and it may also cause a motor to smoke. Usually a short will cause fuses to blow or circuit breakers to trip. Evidence of a short in a motor is usually found in the condition of the insulation. For example, the insulation may be hot to the touch, it may be charred, or it may crumble when it's touched. If a motor has started to smoke, or if it has blown a fuse or tripped a circuit breaker, it's a good idea to check the motor for grounds. This is because shorted coils in a motor are likely to ground. If the test for grounds doesn't indicate that a ground exists, then you should look for a short. You can do this by testing for opens because shorts rapidly become open circuits. Take a moment now to check your knowledge of troubleshooting DC motors. In this topic, we looked at tasks involved in maintaining the brushes and commutators in DC motors. We also looked at ways to troubleshoot a DC motor for grounds, opens, and shorts. Take some time now to try some practice questions that relate to this material. In this part, we'll see how a DC motor can be disassembled for maintenance. When overhauls are required, DC motors are stopped, de-energized, and locked out and tagged according to approved procedures, and in many cases, moved to a workshop. Work area preparations may include spreading a cloth on which to place the motor. The first step in disassembling a DC motor is to lift up or completely remove the inspection covers on the motor end bell to gain access to the brush rigging. Next, the pigtail bolts are loosened, and then the pigtails are slipped out of the bolts. The brush tensioning assemblies are then released, and the brushes are removed. As they're removed, it's a good idea to place them in a separate container to protect them from damage. The field coil leads are then removed from the brush rigging. The end bells are removed next, after they're marked to ensure that they will be put back in the right place. You may hear these marks called witness marks or registration marks. In this example, the end bell and frame at the drive end of the motor is marked with the letter IB for inboard. And the other end bell and frame at the other end is marked with the letters OB for outboard. After the end bells have been marked, a wrench can be used to remove the seal bolts for the bearings, and then the end bell bolts. The bolts are placed in a parts pan or other container to keep them safe. Then the end bells can be removed from the motor frame. One end bell contains the brush rigging, so it must be removed carefully to make sure that it does not cause the brush rigging to damage the commutator. The next step is to remove the armature. Keep in mind that once the end bells are removed, the armature is resting on the motor's field poles. If the armature is dragged across the field pole pieces, it could damage the armature and the field pole pieces. The armature should be lifted, moved carefully out of the frame, and set down on a cloth or V-blocks, or, as in this example, in a pair of stands. This completes the disassembly of the motor, unless your company's procedures require the motor's bearings to be removed as part of an overhaul. If the bearings have to be removed, a bearing puller may be used. Take a moment now to check your understanding of what's involved in disassembling a DC motor. In this part, we'll look at how a disassembled DC motor can be inspected and cleaned. After the motor has been completely disassembled, the next step is to give each of the parts a thorough inspection. The parts of the armature are easier to inspect if the armature is placed in a set of V-blocks or in a pair of stands. A dial indicator can be used to check the commutator for trueness. In other words, to make sure that all of the segments are level with each other. Each segment is numbered to identify them, and then checked with the indicator actually on each segment. The armature should be rotated very slowly, and the readings should be recorded accurately. As a general rule, if the difference between individual commutator segments exceeds 0.002 inches, the commutator must be machined or ground. Next, the armature winding should be checked to make sure that there is no evidence of solder being thrown out of the risers. The presence of solder is usually an indication that the commutator has been overheating, either because of a motor overload or because there is armature winding damage. The area behind the risers should be checked to make sure that there is no melted solder, dirt, or carbon dust there. If any foreign particles are found, they should be removed with an approved cleaning solvent, rags, and a vacuum as necessary. The armature banding, which is the wrappings of wire or string around the armature core, should be checked to make sure that it is tight and intact. The backs of the coils, which are the ends farthest from the commutator, should be inspected for damaged areas, and the insulation should be checked to make sure that it is not cracked, chipped, or broken. After these inspections are made, the next step is to clean the entire armature assembly. An approved cleaning solvent should be used, and all applicable safety precautions should be followed. During cleaning, it's important to pay particular attention to the bearing end of the commutator, the area behind the risers, and the back ends of the coil windings, which are the ends farthest from the commutator. The cleaned armature assembly should be checked for shorts with a piece of test equipment called a growler. A growler uses AC voltage and the principle of induction to detect shorts. To test for shorts, a hacksaw blade is placed over the armature slots. If there is a short in one of the windings, a distinctive sound will be heard. When you conduct this test, Be careful not to touch any of the commutator segments. The windings are insulated, but the segments are not, so you could get a shock if you touch one. After the armature has been checked for shorts, a meg-ohm meter can be used to test it for grounds. The procedure for this is covered in this unit in the troubleshooting part of the motor maintenance topic. To see a brief description of how this test can be made, select Test. When you're ready to continue the lesson, select Go. The next items to be checked are the motor frame and the field pole pieces. Both of these items are cleaned before they're inspected. Special care should be taken to remove all dirt and carbon dust from the areas between the main poles and around the interpoles. Once they're clean, the field coils and the interpoles are inspected to make sure that they're not damaged. If the insulation has become cracked or broken, it can be repaired with insulation varnish. A file or a special buffing wheel can be used to remove any burrs that are found on the pole pieces. Here, a buffing wheel is used with a pneumatic power tool. There may be burrs because the armature was not removed carefully or because the armature dragged during operation as a result of improper assembly or bearing failure. After any burrs have been removed, varnish is applied to the affected area to help protect it from being damaged and then given time to dry. The pole piece bolts should be checked to make sure that they're tight. In addition, the field coil connections and the coil lead should be checked for damage and to make sure that the connections are tight. The insulation should be examined carefully. Any cracks or breaks can be repaired with insulation varnish. The machine surfaces where the end bells mate with the motor frame should be checked for burrs or dings. Any that are found must be removed with a file or sandpaper or a buffing stone. Burrs or dings can cause improper fitting of the end bells and bearing misalignment. Next, the field coil should be tested for grounds. This test is covered in this unit in the troubleshooting part of the motor maintenance topic. The end bells should then be checked for burrs and dings, and any that are found should be removed with a file or a buffing stone. The entire machine surface of the end bells should be brushed carefully with a wire brush or with a buffing stone and lubricant. And the end bells and the bearing housing should be cleaned with an approved cleaning solvent and then set aside. The brush rigging assembly is the next part to be cleaned and checked. As the brush rigging is inspected, the brush holders should be checked for bends and dings. The tensioning devices should be checked for broken parts, and the pigtail connection screws should be checked for tightness. A meg-ohm meter can then be used to check the rigging for grounds. If everything is all right, the motor can be reassembled. Take some time now to check your understanding of how a disassembled DC motor can be inspected and cleaned. In this part, we'll look at how you can reassemble a DC motor after all of its parts have been inspected and cleaned. The first step is to place the armature in the motor frame, being careful not to slide the armature over the pole pieces. The armature should be set so that it rests on the pole pieces. The end bells are then put back in place. The end bell that is farthest away from the commutator goes on first. To help line up the seal bolt holes in the end bell with the bolt holes in the bearing housing, an awl thread is screwed into one of the bearing housing bolt holes. The bearing housing is lined up with the bearing and the awl thread, and then a soft-faced hammer is used to tap the end bell until the bearing is in its housing. The witness marks are lined up, and the end bell bolts are tightened just enough to keep the end bell from slipping away from the housing. Next, the seal bearing bolts are inserted and tightened, and the awl screw is removed and replaced by a bolt. Then a wrench is used to tighten all the end bell bolts until they're snug. The end bell bolts are tightened slowly, one at a time, in a diagonal pattern across the shaft. Then the second end bell is put back in place in the same way as the first end bell. As this is done, care must be taken to make sure that the brush rigging does not hit the commutator. Again, a soft-faced hammer is used to tap the end bell onto the bearing. The second set of seal bolts and end bell bolts are tightened in the same manner as the first set, and the bolts are tightened in a diagonal pattern across the shaft. When the bolts have all been tightened, the motor shaft should be turned by hand to make sure it turns freely. If it doesn't, checks should be made to make sure that the end bells are on straight and the end bell bolts are tight. A DC motor should never be started unless the shaft spins freely when it's turned by hand. If the shaft does turn freely, the next step is to connect the field coil leads to the brush rigging, making sure that the connections are clean and tight. Each brush should then be checked again to make sure that it's in good condition, and then placed in its brush holder. The brush tensioning devices should be set. And finally, the brush pigtail should be connected to the rigging. This procedure is repeated for all of the motor's brushes. As a final test before the motor is returned to service, it's a good idea to check the motor again for grounds and opens. Take a moment now to check your knowledge of how to reassemble a DC motor.